Hey, what's up? I'm so excited. We're going to run an actual proper course in basic mathematics. I have this idea that math can be a hobby. I know it can be because it's a hobby for me. I freaking love math. I graduated with a degree in pure math 14 years ago. Then I went and worked in the software industry. I worked at big companies like Apple and Google and some others. And I met a lot of people over the years who studied math for fun. I think that that's just such an underrepresented category of people. There's a lot of people out there studying math just as a hobby because it's beautiful, because it's fun. Some of the most famous mathematicians that we remember, one of them who comes to mind is Pierre Fermat. He had a bunch of open questions for a long time, including one called Fermat's last theorem. Just this beautiful result that was only proved in the 1990s. He was, I believe, a lawyer. He studied math recreationally for fun as a hobby because it's beautiful and it's good for your brain. I think too many people are scrolling TikTok and not enough people are studying math. So we're going to run an introduction to pure mathematics and introduction to proofs for adults for fun using this terrific book by Serge Lang. Yeah, I invite you all to join and work through this book with me. So if this is your first time here, I typically do a daily live stream. We're actually literally live right now. I just run my daily practice sessions, relearning math and also trying to develop like a higher level of mastery. I know all the math that's in this book, but I am practicing because I'm practicing how to teach. On the one side, that just sounds fun to me, man. Like, it just sounds really fun to be able to teach intro to proofs and all of the middle school and high school curriculum. This is a high school book written in the style of a pure math book. That just sounds really fun. Like, if I didn't have to make money, I might do that just purely for fun as a hobby. Like, work every single exercise in this book and teach it to people. But then on top of that, I'm trying to pivot from a career in the software industry into teaching middle school or high school mathematics. And I have a theory that somebody could run an honors middle school algebra course out of this book. Like, I think that the United States curriculum just really does a disservice to students because we only show proofs in geometry. And we show this weird, watered down version of proofs that uses a table. It makes sense historically why we would show proofs in geometry because the most famous, most successful math book of all time is Euclid's Elements, which proved all of geometry. And it was based in this axiomatic, formal system of math. But the thing that bothers me is that that book also included proofs of things that we would consider elementary math or middle school math, like things like the fact that there are infinitely many primes. That proof comes from Euclid. It's a beautiful proof. And real mathematics, mathematicians who are inventing new math and proving the fact that some new truth is forever true in any universe, we literally send out prime numbers into the galaxy, into the universe, using radio signals or something. I don't even know. If there's intelligent life out there, we think that they would have discovered prime numbers. Like, this idea of prime numbers exists in the world. It's a fundamental truth. The process of discovering truths is something that is common to all math. It's not just something that you do in geometry. Most of us learn math in this pattern matching style where you see a bunch of examples, a bunch of worked examples, and then you follow the pattern. But you don't understand why the pattern works in the first place. For some people like myself, that's harder to just memorize a bunch of patterns and not understand why the pattern works. It feels very arbitrary, and then you get questions like, when am I ever going to use this in the real world? Like, I don't feel like memorizing all these various recipes if I don't want to, become an engineer, or like I struggle to see why we're solving with a polynomials with a quadratic equation or something. And like the truth is that you're not going to ever get paid to solve something with a quadratic equation. Like maybe. I know for sure I've never used a quadratic equation as a software engineer, but you use the mathematical reasoning behind the quadratic equation all the time. I think in every single industry, like the creativity and the method of abstraction and problem solving skills, like general problem solving skills that's inherent in proofwriting, that you get paid for. That's what like earns you the big bucks. It's the reasons why things are true, being able to make a concrete argument, showing high schoolers mathematical arguments. I like to just call them a mathematical argument, is directly relevant to the real world. Like somebody should teach basic propositional logic along with intro to proofs. And then suddenly you have debates. You have like the method of debating one point versus another and logical fallacies, and you get all like you get argumentation in non-numeric settings. Like you get law. Law is so similar. Like a legal case from an attorney is so similar to the axiomatic method. You have definitions, you have connectives, like if this, then that. You have previous results of previous laws, and you try to combine two different laws and show how this example, this case is an example of these two different laws applied together or something. At least that's my understanding. I've never taken a single law class in my life, but I know that mathematics as a major is one of the best majors for a pre-law degree. Yeah, and so I'm just super excited about this. In stream, I'm going to do 1 week on middle school, high school fundamental math. Then I'll do a week of streams on college level math of calculus and linear algebra and maybe some others. And then I'm always structuring streams to have 1 week of graduate level math, where I'm learning new math. For a while, we've been working representation theory, which is applying linear algebra to the mathematical study of symmetry, a very beautiful field that I'm learning live. So that's the structure. We're changing the stream structure to have more high school math, middle school, high school math, pre-calculus. We should just call this a pre-calc book. This is all math before calculus, I think is accurate. But it's done right. It's like done well. It's written in the style of a pure math book. I like it so far. I'm not too far into it. But so there's the practice sessions that are live. Then during these weeks where I'm working fundamentals, I'm going to be filming proper lectures without chat, but it's going to be a lecture on a section, and I'm going to try to follow a syllabus. I'm going to try to follow like a lesson plan, preparing for someday when I get a classroom of my own and I get to teach the little children pure mathematics. I'm excited, and I invite you all to follow along with me. Get this book. It's terrific, by Serge Lang. It's hard. I mean, it's a hard book, but like if you're the kind of person who likes to solve Sudokus, or if you're the kind of person who like you didn't feel like you did well in math in high school and you want to like come back and conquer it later on as an adult, like dude, this is such a better hobby than scrolling TikTok. Like, get off of YouTube right now and go get this book and go work the first 2 exercises. They're actually harder than you might think, but it's literally just addition. Let me show you. I can put this up to the camera, fair use and all that, right? Let me show you the first exercise set. Like, these are the very first problems for this book. And I think that somebody could teach an honors Algebra 1 course in middle school using this book. Dude, those are the very first exercises. Justify each step using commutativity and associativity and proving the following identities. A plus B plus C plus D equals A plus D plus B plus C. Like, some people say like, oh, math lost me when everything turned into letters. And I think that's a shame because we wait too long, in my opinion, until we start introducing letters. That's what real math is in some sense. showing that for any numbers, this pattern always works. And there's a concrete, clear argument why. Yeah, so I'm excited about this. We won't only be using this book, and I'm going to be jumping around like all over the place. In the foreword of this book, Lang recommends that you jump around as a teacher, which is awesome. This is another thing where I think that the US curriculum is, I can only speak to the US because I have only ever lived in the US, but we go very depth first, and we teach students to work 30 exercises from the quadratic equation or something, and then we do 30 more problems on something else about polynomials, or like completing the square to solve quadratic equations or something. I just think it's so much more valuable to jump around. Like, why don't we show matrix addition immediately after addition? Like, you can add two numbers. Like, you can add 1 plus 2 is the same as 2 plus 1. Turns out that in math, you can also add blocks of numbers. 1, 2, 3, 4 in like a little grid, plus 5, 6, 7, 8. You add 1, like the top left numbers, and that's the new top left number. You can add the top right numbers, and that's the new top right number. You can add the bottom left and then the bottom right. And this forms a new field of math called linear algebra. And it's just the very beginning of this really incredibly beautiful field of math, which turns out to be, speaking from experience as an engineer, the most useful math in the world right now. Why don't we introduce that immediately, like with addition? Is that kind of crazy? Is that crazy? I think it's a good idea, because then it takes a little bit more work, but you can define multiplication of two blocks of numbers, and the regular numbers satisfy a times b equals b times a. Like 2 times 3 is the same as 3 times 2. But blocks of numbers don't work that way. Block 1 times block 2 does not equal block 2 times block 1. Having examples from quote-unquote more advanced math or different math, different fields of math, and then contrasting that with a simpler math, I think that can be a really effective way to teach, at least for the right student. So I'm excited. Join me for this. Keep an eye out for lectures. I'm going to be posting these. This video is already longer than I planned. I should cut out something, but hey, it's live, so these things happen. Thank you for watching, and see you sometime in the streams. There's also going to be a paid group lessons, and we'll figure it out as we go. I think it's going to be Zoom classes on Saturdays, ? So if you want to hang out with us in Zoom and work some problems and ask questions and meet fellow math hobbyists, there's your chance, dude. Like, we already have 3 people signed up so far, and it's turning out to be a really nice little group. So hope to see you there, and if not, feel free to follow the public free videos. I'm looking forward to this. Like, I'm genuinely, for myself, looking forward to working the exercises from this nice yellow book. So thanks for watching. All right, see you around.